Okay, thank you for giving me the opportunity to talk on behalf of our organization and also some of the contributions that we're allowed to share and to contribute to the GNU Radio 4.0 code base. In this presentation, I want to highlight who we are, why we use and invest into GNU Radio, and then a slight motivator why to move towards the GNU Radio 4.0, mostly showing some of the technical highlights. I have to apologize, I have to keep this very brief, and I can show you just a few highlights and I have to skip over probably some of the items, but there will be like an answer in a Q&A session this afternoon where you can go a bit more into the details and you can ask me anything about what we did and why we do it and what the next steps would be. So GSI is located in Darmstadt, Germany, and has been a key player in heavy iron research since 1969. And it's part of Germany's major research infrastructure that is funded by the federal government and the state of Hesse through the Helmholtz Society, which is basically the German equivalent of the Department of Energy here in the US. And on the photo you can see on the lower left the existing facility, which is a national laboratory, which is now also hosting FAIR, the Facility for Antiproton and Iron Research. FAIR is an international extension funded by 11 member states, so we're not just national, but we have mostly European, but also India and Japanese contributions. And its main mission is to provide an accelerator-based fundamental research platform for nuclear, astro, and plasma physics, as well as applied biomedical and material science applications serving around 3,000 visiting scientists from about 50 countries worldwide. So many wonder what we do. That's our slogan. We explore the universe in the lab, or maybe. And what is meant by this is like we can recreate rare cosmic processes that naturally occur across our universe, like those observed using, for example, radio telescope that you heard earlier about. And our focus is that our accelerators can basically act like giant microscopes and allow us to directly study these processes that occur on a galactic scales using RF signal-based processing other detectors, but however at a much higher event rates and precision than what you can do with sky-based systems alone. So using particle accelerators, we aim to unravel some of the most fundamental scientific questions. The mysteries of our universe, what are the smallest building blocks of matter, and how, where, and when were they created? And notably, while we and everything around us is made out of regular matter, the big question remains, what happened to antimatter? And we know it exists, so why does nature seem to favor regular matter than antimatter? And we're trying to recreate antimatter and see then the asymmetries between the behavior of all those two. So connecting again to space, we study processes that occur in space on a regular basis, and we also look at processes that created the elements that we see around us today. And by looking at events like supernovae, we explore also those elements, how these elements, heavy elements like, for example, gold or uranium, are formed in stellar explosions. Another key area that we're looking at is matter under extreme conditions, like those found, for example, in neutron stars or processes that occur in black holes. These are some of the densest objects in the universe where matter behaves very differently under intense gravitational forces. And with our particle accelerators, we basically can recreate and explore those extreme conditions, but in the lab. And at GSI, on FAIR, we have the unique ability to study exotic forms of matter in ways that were once impossible. We can selectively produce, accelerate, and store protons, antiprotons, rare isotopes at unprecedented event rates and energies. And as you can see at the plot, that basically like a bit our menu, what we can provide. This is basically like if you unfold the periodic table of elements, you have on the vertical axis the number of protons which define the element, and in the horizontal axis are the isotopes. So they vary only in the number of neutrons that you have in the core. And many users, by studying the decay processes of these isotopes, you can infer certain processes that also occur at galactic space scales. And yeah, basically people come, point, and say, like, please, can you produce this at this rate? and we have a very high selectivity. So when people ask us, which particles do we accelerate? Anything from protons, antiprotons, up to super heavy elements. And also we created 6 of the rarest elements first observed at, in our labs, like funny names like Darmstadtium, named after the city next to where we hosted, or Hassium, named after the state where we're located at. Of course, there's much more to do. We're not just doing fundamental science, but we're also a technology forge. So many of the things that you need in science, also you need to advance technology to be able to measure those very rare effects. And beyond fundamental research, our heavy ion accelerators have practical applications, like, for example, cancer therapy. Developed at GSI, heavy ion therapy has treated hundreds of patients and is now in clinical use in Heidelberg and Marburg and many other facilities all over the world. And it's a great example how basic research can also lead to life-saving innovations. Because we can create such a large spectrum of different particles, we're also working together with the European Space Agency to study space radiation long-term effects on humans. ESA also wants to send people to Mars, but contrary to Elon Musk, we also want them to be healthy and also come back alive. So we see what we can do about this, and a lot of testing of radiation-hard electronics for future Mars missions, but already some of our electronics and ASICs that we designed are now making their mission towards Jupiter as part of the JUICE mission. So just like a few impressions on what to expect in our facility. Some of you have visited us, and we were very, very happy about this. This is our universal linear accelerator, and is the first particle accelerator in a chain. It plays like a vital role in initiating the acceleration process for many of our experiments and many different particles that are required. So it's very, very flexible. And in the middle, you can see Sharp. That's probably one of our longest standing SDR users. And this picture is quite old, so sometimes I wonder whether he was maybe part of the founding committee of FAIR. But yeah, this is very important. Eventually, linear acceleration becomes inefficient, and you start, okay, this is sorry, I forgot, this is a picture of the UNILAC internally. This is a very rare view from inside, showcasing the massive size of our resonating cavities and the vacuum tank, and just for scale, you can see a human inside an accelerator and inside a cavity, which you don't have often in the world. But this is usually a very rare image, because most of the time, because of this particle, are very reactive with particles in air. We have to keep the extreme high vacuum in our particle accelerators, even less than that you would find in space or on the moon. So, yeah, eventually linear acceleration has its limits, and then you need to accelerate in ring accelerators, basically where you have the same cavities, but you bring the beam around over and over again. This is the SIS-18. This is our versatile workhorse and ring accelerator. And it provides basically booster mode to various experiments and applications, and the flexibility of this accelerator is key, and it has to be adjusted in a multi-user, multi-mission mode on timescales of changing the operation mode within a few seconds or sometimes even milliseconds. So with our current setup at GSI, we've achieved quite remarkable results, but in order to meet the growing demands of modern science, we need more and more. That means more power, more particles, more precision, and more versatility. And that's why we are upgrading with FAIR. FAIR will increase both the particle intensities 10,000 times, boost the energy levels that we can achieve, and allows us to explore even more exotic states of matter. And this upgrade is essential for us to push the boundaries of what can be studied and discovered, and also to remain competitive in science. This is a few schematic overview of the FAIR facility. At its heart, you have the SIS-100 ring accelerator, which spans about 1,100 meters circumference. And this layout is specifically designed for multi-user parallel operation, showing frequent reconfigurations for the facility, accelerator and particle beams to support a wide range of experiments simultaneously. Running FAIR means also what I mentioned is means that we have to continuously adjust the accelerator settings, beam parameters, and equipment in order to accommodate our users that are operating the experiments at the same time. And GNU Radio is part of managing this complexity. at our facility. This is like a view of how hopefully soon the site will look like once we replanted all the trees. And FAIR provides a cutting-edge infrastructure that pushes the boundaries across multiple scientific fields. And yeah, I forgot to mention, it's about like 2 kilometers in diameter, the whole site, so it's quite impressive. And we hope that FAIR, like GSI, will continue to be a game changer for physics, chemistry, and beyond. Now, if I would get $1 for every time I've been asked why we use GNU Radio, probably I could have funded like another particle accelerator. And many colleagues ask me, both external and internally, why do you use GNU Radio? What is GNU Radio, and why we have chosen to use it at GSI Fair? And I thought, like, let's break it down step by step. Maybe this is a bit of preaching to the choir because you all know, but I try to put like a small twist why we use it for particle accelerators. I think one of the important cores is because it's a free open source. It's a key aspect, that it's an open source platform, because this allows us to better interact with our visiting researchers and scientists, also with universities across the world, and also to liaison with industry, because while we do certain developments in-house, also like electronics design, we want to engage more with the industry and also enable them to use the technology to put it into real production use in industry, be it automobile, be it telecommunications, be it radar applications or other things. And we said, like, okay, I'll come back to that later. There's also like a general society civic duty that we should do and why we follow this up. The other thing is people say, like, radio. You're running particle accelerators, why do you need radio waves? So at its source, radio is a software-defined radio framework, which originally has been developed for traditional radio frequency application. But, and basically when people think of radio, they always think about this dipolar antenna or other shapes that irradiate RF. But we use RF extensively to shape and manipulate particle beams as part of our radio frequency cavities, because we accelerate charged particles. And manipulate them also using strong RF fields. So we have a RF power of a few 10 to 20 megawatts to do that in our facility. But also, most importantly, is we deploy a wide range of diagnostics tools, from very low radio frequency to up to gamma rays, invasive and non-invasive techniques. And as a nice feature is, if you want to do like a non-invasive measurement of particle beams, you basically observe, when you have ever-moving charging particle beams, they drag an electromagnetic field along inside the accelerator, which is proportional to its beam properties. And what we do is, rather than pointing the antennas out and looking for particles in space, we point them inwards and looking at the properties of the beam, and first of the field, and then can infer properties of the beam itself and the particles themselves internally. Another important aspect is this paradigm under which GNU Radio works. These are flow graphs. And this helps us while we have a lot of people who have the domain knowledge required to operate particle accelerators and people who know how to do their signal processing and correlation and high-level physics. Not every one of them is a research software engineer. So there's a difference between getting the job done to receive your PhD and to be able to maintain and run a software to have a 24/7 operation. And using flow graphs, this is for us a common denominator where we can speak the same language on a high level, but without losing performance due to this abstraction. And this is for us key, and I'll come back to that later, because this enables us not to have a few people who can write software in our facility, but this enables like tens to up to 100 people more to help to make a meaningful contribution to our facility operation. And that alone was the main reason also why my boss said, like, yes, please do that and continue on, because that makes a better use of our resources that we have in-house, and the free new resource we can use for other topics that we can advance new detectors. Important is, obviously this is not a self-serving purpose. We want to have high performance computation, and GNU Radio 4, what was important for us, we use this also in our feedback loops. Feedbacks are real-time systems where the answer that we're getting out of the signal processing is not just the where the correctness doesn't just depend on the value of the result that you are getting, but also the time in which you get this result, because we want to react back and put those information into the accelerator to improve our performance of the particle beams. And last, certainly not least, we are not alone. And GNU Radio brings a very diverse community and more than 20 years of expertise in terms of signal processing. And now with GNU Radio 4, it's like modernized for today, where we said like we make an active investment rather than reinventing the wheel. We felt that our goals are in line with the vast majority of GNU Radio users, and said like, okay, rather than building up a second ecosystem for our 10 to 20,000 users, we thought like, let's invest into GNU Radio and share some of the opportunities together. And yeah, sometimes good ideas are equally created in different domains, and just by communicating and sharing these ideas, we all get better collectively. So that was an important aspect. So that's basically in a nutshell. And then what I wanted to say, there's a couple of more slides where I can show you some nice examples in terms of pictures. We also do beam forming. We call it bunch merging. For example, what you can see here is where we have like bunchlets of small individual beams that are gradually shifted together using RF forces on our cavities and then are merged into one bunch. That's one of the examples. This is an example now in the time domain, but we also use like spectrum monitoring. This is one of our fixed displays that our operators are looking and will be looking at to fine-tune the distribution of the particle beams. In this case, this is a Schottky spectrum and shows us the beam momentum distribution, and this is used to synchronize, for example, the properties between the UNILAC, our linear accelerator, and our first ring accelerator, SIS-18. And by keeping a track of these energy deviations, like the center frequency of these carriers, but also the width and shape of that, we can improve the beam parameter performance. Another exciting topic is accelerators by themselves are also used as detectors, because while the particles traverse in their on the circular trajectory, in the trajectory around the accelerators, we can do very high precision mass spectroscopy. And for that, we deploy very sensitive, high gain antennas or resonant pickups that look at the revolution frequencies of the beams that we store in the particle accelerators. And they're so sensitive that they can even detect individual particles. And by measuring the revolution frequency of the different particles, we can make a mass spectroscopy of the different, not just elements, but also of the isotopes and even like excited states of these elements. And because we can measure individual particles, we can also do time-resolved measurements where we can measure nuclear processes in air, in free, which is very rare, as a time-resolved, as a function of time, which is very valuable because most of these reactions, if you don't have an isolated ions, they're typically absorbed in some form of matter, so you can't observe it any other way, just inferred by the secondary process. And this is a direct measurement of a beta decay, which emits the neutrinos. Now, the name of the game is, our upgrade goals is to shift more and more towards from post-processing that was done largely offline to go online. And one of the ideas is also to use GNU Radio as an active component in our decision-making process, where basically you operate, this is an idea by Sharp, where the idea is to use GNU Radio for routine monitoring and recording of the data, but also shifting more of the pre-processing already in the front end. But if we find very rare isotopes, which sometimes are generated only once per day or once per week, that we can select, oh, we found something, using an early detection scheme in the GNU Radio chain, and select, please stop. Please stop, don't inject, don't dump this beam. We want to store this beam for a couple of days and do like more detailed analysis. And that is a powerful tool, and that is ultimately worth of generating several millions worth of signs in a day. Yeah, and this is like one of the science applications, but we also use it for just operating our accelerators. Beam-based services are critical for the operation of accelerators, and you can see basically the scientific users are king, and they expect basically a wide varieties of particle beams with several different properties. And in order to achieve these properties, we need feedback loops, and we're using GNU Radio to implement a very flexible signal processing layer that allows distributed real-time data aggregation and sanitization and post-processing across thousands of devices. So we're dealing with 10 to 100,000 signals. And these are then piped to middle-tier services that do aggregate and correlate the data from different detectors and use to feed back into the accelerators to fine-tune the magnets and the RF cavities. Yeah, this allows also like software-based feedback applications. Okay. So this slide's highlight a bit like the integration of GNU Radio within our open source framework, Open Digitizer framework. Open Digitizer simplifies the digitizing signals from a wide range from devices, not just SDRs, but also oscilloscope, network analyzers, particle counters, scintillators, across the GSI fair site with a target number of around 300 to 400 front-end computers or nodes and a couple of dozen middle-tier services that are distributed across the network. And these nodes feed their meta information into the dynamic name service, which is basically a catalog of roughly 100,000 signals that the experimental users and operators can choose from. And that where basically is a catalog when say like, please give me this and the signal, and then we transfer the data to, for example, either another middle tier service or an Open Digitizer UI, which is still work in progress, but is designed to function like a distributed oscilloscope or spectrum analyzer, providing real-time monitoring and diagnostics. The key here is because we have to be very flexible, and sometimes we have to have provisions for the unknown. So some of the facts we can't forecast. I mean, we have a strategy, we prepare most of our data processing chain, but sometimes you have to adjust on the spot to meet a given problem or challenge. And the key here is that we use GNU Radio not just in the digitizing front ends, but also in the middle tier service and in the UI. So if somebody in our control rooms want to experiment, they first could try this in the UI, and if they say like, oh, that's a nice flow graph, but I don't have enough processing power in my end device, please shift it to a middle tier service, or if it's very high performance and I need processing on the level of 250 or 500 megasamples per second, then we can shift it further down to the front ends, and if this is not enough, something that we're working on that we can even like dynamically shift it onto an FPGA on the fly. And this allows also serving with the same device multiple users at the same time because they all look at the same data and reuse the same device. Part of that is our open common middleware, OpenCMW, which implements basically a major domo pattern, providing a common abstraction layers across multiple transport and serializer protocols. Like in a nutshell, it's an open source and streamlines get set, pubs up communications with our open digitized infrastructure. And the main reason is there are many middlewares out there, but this one is designed to be adaptable, that it can wrap different transport protocols and serializer protocols and provide the same high-level user interface for writing services so that you don't have to reinvent the wheel and adapt from MQTT to different REST services through 0MQ and so on. So yeah, key is one is like the transport layer, but for example, GNU Radio is then used also as one of the workers, and the serialization is implicit, can be explicitly specified, but the user doesn't have to care for the how the data is getting in and out. This is taken care by the OpenCMW middleware that we have, and exists both in C++ and Java. Yeah, looking ahead, we're working on expanding cross-platform support to make this user interface more accessible and customizable, and to work also natively, not just on the desktop, but also on the web. And this allows us to modify signal processing analysis both on the UI and the remote front-end controller. Maybe this is not maybe as fanciful as Luigi's example that he showed, but our focus was mostly to provide like a dashboard-style a view of not just frequency data, but also scientific data with units. And the idea is that it's like, has to be adaptable. So you can modify this on the fly, and yeah, it's available on the mobile platform. These are just some screenshots from the devices. So basically you have the possibility to modify the blocks on the go with the standard GNU Radio blocks. So these blocks, in order not to intimidate people, we try to use the same look and feel of the existing GNU Radio companion, but in C++, but underneath it's the same, I guess, the IMGUI node editor, so this can also be made look more fanciful, but we deliberately choose a traditional look so that people have a better relationship to that, or that they recognize the structure. And yeah, there we can both have modify the visual layout, but also the flow graph, and then also create a catalog where you have standard views that can be stored in a catalog and then recalled for different users and applications. So why did we invest into this? For us, GSI FAIR uses, supports, and promotes FAIR. That's the standard. So we do open science and FLOSS. And part of this FAIR acronym is also the interoperability and that R stands for that you can recreate and revalidate the results. So the idea is like, in German you say like, okay, if you make the measurement once, it doesn't count. It has to be repeated also by others and verified that this is not a systematic or instrumental effect. So this interoperability and repeatability is key of open science, and it's also part of our mission, and that's the reason why we invest into not just open science, but implicitly also like open source and free source. And particularly for GNU Radio, this aligns with our primary goals. I mean, we contributed not just for the sake because we had not enough time to do, but this solves for us a very specific purpose of high performance continuous and event-based signal processing, also event type data processing, which turned out to be very similar to packet radios. And yeah, with this visual flow graphs, this helps us to bridge the technology gap between people who are experts in their respective domains, signal processing or particle physics, nuclear physics, and the people who know research software engineering, where unfortunately we don't have enough staff that can cover both areas in equal measure. So this helps us, and yeah, to have more staff and users to contribute to GSI FAIR. But our contributions are not just within FAIR. We also have an active engagement with industry and other public organizations. And this helps us reinventing the wheel, simply by co-investing, sharing, maintenance effort. And what's important for us, also as let's say as a state-funded organization, is that we want to invest into open standards, because that is can be very costly things if you diversify, and this helps us also like to build up competencies, because we do state-of-the-art development and working not with legacy standards that are 20, 30 years old, where it's very hard to motivate people, because people know we work with C++20. We have 2 members that are core members of the C++ standardization committee. People come to us and say like, oh, what you're doing is cool, and can I work for you? So in the beginning we had a hard time recruiting, finding the right people, and now basically we don't have to do active recruiting anymore. People apply to us and ask, do you have a position open? And I think that's also like a very powerful experience, I guess, for the industry and other labs that are in this room. This signal flow graph processing concept is not very new. It's very old. I mean, like I looked into what was the origin. It started actually with Bell Labs, so it's always surprising how much was developed at Bell Labs. So there was originally Bloody, and the people built this tool for the very same reason that we use it today, because they said like, it's too expensive to build a hardware. Let's do some prototyping first in software. If it works, add more and more components to it, and then in the end, if we need to combine this, we take this knowledge and build the real hardware and standards to be sure that it's viable. And based on this idea, directly spawned also like SPICE, also flow graph based, and other companies like MathWorks or National Instruments also opted for a similar approach, and Siemens. What is maybe important to note is GNU Radio arrived in the early 2000s, but the main thing is, compared to all the previous solutions, is that's open source. So it's unbiased, it's free, everybody can use it, and it's vendor neutral. So you don't have this vendor lock-in, and you don't have to reinvest over and over again into the same idea, same technology. And it's continually been used also like in gaming industry, like Unreal Engine and Unity, and our hope was like to modernize it and make it ready for the next decades to come. So just to explain this, I'm like now in most of the communities, the reasons why we invested is, I'm like many of you use it to express certain ideas. They have a conceptual idea and say like, okay, how can I transfer this into a concept using flow graphs as an expression as a first starting point, and then you basically iterate back and forth, use it maybe more as a simulation tool. Once you know that the simulation works out, you say like, oh, let's build a basic prototype, which we also do. And there, I should point out the mechanical sympathy was for me very appealing because I'm coming from RF engineering background in physics. And seeing all those little connectors on those blocks, I'm like, ah, yes, that's like a LNA amplifier that you can buy off, for example, mini circuits. So that helps also like our RF engineers to connect to this concept much more readily. But then sadly, like the traditional sense was like, there was like a barrier. So whenever people develop the prototype, they say like, okay, let's take that knowledge, throw everything away, all the years of prototyping that we had, and write everything from scratch. That's costly. That's costly. Maybe you get a better integration, but you wasted lots of investment that you put in. And for us, the GNU Radio goal, zero goal was to remove these barriers from going from a prototype to an industrial operational deployments and to achieve a wider public adoption. And then if you want to do this, this is only possible through showing that you get better performance and functionalities, but also help it make it a dependable system that can be used in 24/7 operation. Why invest into GNU Radio for zero, and particularly why to implement a lean, clean, and secure coding practice? That should be self-evident. So when you ask people, yes, should your code be clean, should it be lean, and also secure? Everybody would say like yes. Who would say no? I guess I don't want to put on the spot. Everybody, I guess this we can all agree. But unfortunately, often it isn't. Because either collectively we said like, okay, I have to get a job done and I have to move on. And then we only look at the cost at hand that are immediately in front of us. And there's like a very nice IEEE article. This is linked below. I invite you to look at this. This is referencing an article that is 30 years old, and internally you have another article that is 50 years old. The problem that we're facing today is the same problem 30 to 50 years ago. So Melvin Conway wrote a paper already in the 70s, and I make it feel sad that somebody who wrote about this well before I was born and said like, this is a problem we need to address. And we haven't managed to be able to address it. Why? Because people think only at the immediate cost and they don't look at the total cost of ownership. There's a price of doing something, but what many people forget is also a price for not doing something, to omitting doing it, because this will come back. If you don't write clean software, you have certain challenges and risk. For example, if you have a code base where you just add to it, the larger the code base becomes, the more non-secure your code base increases, and this also increases the cost and risk for maintaining this code base until it blows up. And the standardization effort is very important. Was recently an NSA lecture released to the public by the late Admiral Grace Hopper, who worked on standardization across different fields, and that she said like, also there's a price for doing something, also for not doing something. And she said like, what is the most scariest thing you can do? Who are the most scariest people in the US that you can ask? And she went to the Congressional Budget Accounting Office, and they looked into what is the cost of having a heterogeneous standard. At that time was like COBOL, but I think it applies also today to other standards. And they figured out by having not vendor-neutral implementations costed the United States $240 million every year. We're facing the same thing, the same problem today. Maybe this were like 1970s cost, now they're much higher. And on top of that, there's a risk also in terms of security, because using software is ubiquitous, especially software-defined radios is used in many applications, also safety-critical application. And the risk for critical infrastructure, we know that the Eastern Pipeline is a good example. Recently, we had like a major incident with Microsoft that shut down half of the world because of a simple coding bug. Now you can say like, win of the job, not my job award, and maybe I try to hide and blame it somebody else, and say like, was not my fault. Or the other thing is, and which I think is the right thing to do, is to step up and say like, take charge. We have the possibility to address this problem and work together. And so I don't want to be too gloomy, but I think there's a great opportunity in GNU Radio to share in this responsibility. I mean, like, nobody is alone. Nobody asks you individually, oh, you alone have to fix the world's problems, or you have to do everything in GNU Radio. But if we pool our resources together and work together, we can mitigate some of the costs for having a continuous improvement and keeping our code base lean and clean. Also that if it's lean and clean, it's easier to audit and get security certifications. It also helps to improve the bus factor and burnout for core maintainers, because that's one of the biggest risks, that people say like, no, I don't want to do it anymore, and then just leave. And then you lose a lot of corporate knowledge and expertise, and also motivation. We can do something against it together. And the idea, that's my message, I want to say like, let's promote GNU Radio as a free and open industry standard, where we all rally behind and say like, we invest together into that. Because if we don't, their governments, both the US White House, the White House in the US, but also the European Union, have already legislation that says like, if you don't take care, please be proactive. Both in terms of the Cybersecurity Act in the European Union, but also in terms of product liability. If you're not proactive, the legal system will tighten up the thumb screws more and more. And I think this is unnecessary, because we don't want to get the government involved in terms of legal aspects, because they have ultimately no clue about how to regulate low-level technology. So, yeah, for GNU Radio to be used in a critical public infrastructure, or I believe any real-world commercial applications, it must meet higher standards for safety, cybersecurity, and product liability. And I encourage you to take charge and do something about this. So now a bit like the technical highlights. I have to go through this a bit faster. Sorry if I skim through some of the details. I mean, I started everything like, not in the mid-2002, sorry, it was mid-2022, when Derek Kosel and Josh Mormon, basically whatever is good, it's their responsibility, and they approach us, oh, you use GNU Radio, why do you use it for particle accelerators? And at that time we used GNU Radio 3.7, and we had some issues and tried to do some workarounds, and then both Derek and Josh said like, why? It should be easy to solve, and Josh, single-handedly, within 2 weeks, he solved the problem of this compile time reflection of being able to use GNU Radio just in C++ without the necessary Python binding. And we thought like, wow. And then they came back, and maybe that was a mistake. Josh, please, I'm sorry. was if you had the chance, were there other things you would like to change? And then we said like, well, since you ask, we have this concept of event-based processing, and after some discussions, we realized that's the same problem as packet radios, that what Danny now is implementing. And so like, oh, that's the same problem, why not work together? And we had many more discussions on the GNU Radio architecture channels, and then basically highlighted some of the pain points that we thought like with the GNU Radio 4.0 we could address. Importantly, we said like, we don't do this alone, but we do this together in a collaborative spirit. And said like, okay, let's look at the buffers and computer-related performance, help making asynchronous event processing basically a first-class citizens of GNU Radio, and also the scheduler to be able to make it more flexible, so that you don't have like just one way of how to run and schedule processes, but that depending on the application, you can tune between throughput and latency. Also, the idea is to make it easier for integrating vendor-neutral hardware, but also heterogeneous distributed or embedded computing, and also to help the GNU Radio community to grow, to make developing blocks easier, safer, leaner, and cleaner, and easier to maintain on the long run. So community building is very important, but also the building up a technical also while maintaining a technical relevance. I think we didn't want to create something that is not GNU Radio, so that was always core. And there were like certain underpinning things that needed to be done, like reliance on true hardware, real hardware or true industry standards, reducing the cognitive complexity, because now the learning curve getting into GNU Radio, once you're in, you say like it's easy, but getting into it is very high. And yeah, work together, not just academia or science, but to do this all together with the government and the industry. Important, if it's worthwhile, it has to be technical relevance. That's the reason why performance was key. And the next few slides I showed like what were the performance gains that we were able to achieve now with this with the GNU Radio 4.0. So I'm not just going through. One is like safer, leaner, cleaner API. We moved from a framework where basically where you have a prescriptive framework where you could exchange blocks, but they always had to have the same shape, but maybe different colors, to like more modular approach. I call it like the Lego assumption approach where you can, which is performance and functionality focused, where you only have to pay for what you need. That's like a part of C++, which is free to extend and modify, but also that is compatible and auditable, and that can be used with a public infrastructure. So I think the important part is like to preserve the concepts. And what we did together in the architecture team, this was also led by Josh and others, was to highlight what is a block, because we didn't want to have something completely new. So we thought, what are the key essence? What is a block? What is an input streaming port? What are tags? The same thing, you have the output ports. So we tried to not define new, but to select to sharpen the definition. What is each of the different components supposed to do? And how can we implement it most concisely, most efficiently in the different domains, so that it's composable and that you can exchange also the implementation. And also looked on standardizing what the message port, which used to be like a control port, where we said like, okay, let's get rid of some of the heterogeneity and make it more streamlined. And that's basically the result. If I need to teach how to write a block in GNU Radio 4, that's one slide. That's not slideware, that's actually part of our production code, part of our unit test. That's all you need to know. You need to describe the input ports that you want to have with the type, the output port, and your processing function, where you say like, I get my input data, and you write a pure mathematical function. Anybody who can understand math or write basic physics can write a function that executes the processing that you need. And because it's lean and clean, it's easy to learn, but it's also easy to audit. And can be also used better by compilers to optimize the whole chain of how you string those functions together. There's often also the possibility to extend it to heterogeneous computing, like for example SIMD. Or if you say you want to have more like the traditional sampling aspect, you can also have process bulk functions where you get chunks of data, input and output, where basically the rational resampler is a first-class citizen. So this is like let's say, a more advanced level of API. And then you can also make it even asynchronous. You can declare how many samples you consume or you produce. This is not slideware, this compiles. So we also tried to keep conventions with the GNU Radio companion in order to produce YAML files. Describe this topology. On the left side, you can see a topology for basic flow graph. The blocks in the top, connections in the bottom, and within GR4 you can read and write those definitions and execute it. So any integration in UI should be simple with that. And but while we have like let's say, a UI for our purposes, I think this UI and UX integration and Python bindings need to be community driven. So this is somebody from you has to step in and make a proposal how to do this best. Similarly with Python integration, for us was always important that we can also integrate it with Python. There are two ways: either you have Python within C++, or you use Python and you call C++ from that. So there's two paradigms. This is an example where we have a Python block which you can instantiate in your flow graph, and the processing functions are written in Python. So this is not for Python plumbing, but for the part where you can use NumPy and other features to derive your features. Yeah, everything is compile time reflection based, so single source of truth. We don't have a separate documentation of code and explanation. Everything is in the source code, and you can generate automatically documentation. If you want to know more, there was recently like a workshop with lots of good tutorials, and you can find it on YouTube, both on the GNU Radio YouTube channel. Okay, buffers, important. If you think about like mechanical sympathy, that's a concept that we followed. You don't have to be engineered to be a racing driver, but you do have to have mechanical sympathy. So more general, in order you want to optimize your processing, you have to understand on how the machines you're working on itself work to be able to get the best performance out of the machine. And that means basically you have to know how do chips and CPUs work, and how does the architecture look like? Because with this way you can get a better performance and structure your code in a way that you get the best out. I think I skip over this. Everybody knows what the difference between bandwidth, latency, and throughput. If you need lower latencies, basically you need either higher I/O memory bandwidth or minimize the critical data sections. There's an example between like what is concurrent and concurrent parallel. Typically, the latency is defined by the longest time it takes to execute a certain functions. This is in the ideal world, but often you have like certain overhead due to context switches and systematic overheads due to the different constraints you have in your operating systems and your CPU. And typically, the classical paradigm in GNU Radio 3 was you minimize the impact of this context switches and overheads by just computing more and more data so that you have the calling of the functions higher. As low as possible, but the problem is that this is a very bad strategy for latency. So if you want to decrease the latency, you have to tackle actually what are the sources for this context switches, or maybe avoid them at all, that you don't need them. So that was the main goal of our redesign of the low level, and looking onto the different caching strategies and optimizing it. We don't have to go into this, there are some links. So for the buffer, basically it has the same thing, but it deploys this principles on a much lower level. Maybe two noteworthy things is there are new features. You can now safely and efficiently propagate both unstructured safe data types, so no more null pointers or void pointers, so that should make it safer and more secure. But the new buffer also allows to transfer structured data types. So that is like used for the event-based processing. And in addition, because of using a log-free programming, which is SIMD and also CPU optimized, we could achieve a 10 times performance just for the buffers compared to GNU Radio 3.10. We also moved away from virtual inheritance and went to strict typing and CRTP concepts. I don't want to go too much detail, but the way how we write code is easier to optimize by the compiler, and that's one of the reasons why the performance, just because of this move, is also like yet another factor 10 faster. And the best buffer, if you want to go for low latencies, the best buffer is if you don't need a buffer at all. So we introduced like a merge API where you can combine functions across different blocks into one block without paying extra overhead, but still retaining the syntax and the meaning on what is the logical functions that are concatenated. Just some performance figures. You can see like in red, this is like a factor. You're going from something 250 megasamples per second. We achieve typically with this runtime polymorphism up to 500 megasamples per second, but now with certain flow graphs, we get even like in the order of a few 10 gigasamples per second. I think that was not yet possible in the GNU Radio 3. Let's go. Okay, asynchronous event-based, I think I skipped this over because I think that is, clear that structured data can be used to basically do multiplexing and chopping the data out of the data stream. Key takeaway can be used to process any structured data type, and this you can also develop feedback loops or packet radios very efficiently. And the idea is to extend this further also to the UI level, where you can program certain feedback loops similarly to what you find, for example, in the gaming industry. Data synchronization, these two clock problems, is also solved via standardization of the triggers on the tags. I think that's clear how that works. I think what is maybe more important, what many people ask, like the scheduler, it was very important. There were like basically two limiting factors in the GNU Radio 3 design, the main pain points and reason why the GNU Radio 4 development started. One was that every block is also like a Stutz thread, and their processing function is basically managed by the system scheduler. And the problem is that basically all the blocks were competing for resources. So you had 10,000s of blocks, even though the CPU could, or your system could only execute 4 of them at a time. And then invoking those threads and checking out, can I run and process data, was wasteful, and basically you lost a lot of performance just because of that. And also because the blocks in themselves didn't know about the topology they were embedded, so most of the blocks took a maximum, couldn't take the maximum minimum buffer data into account, and this created undesired latencies because they tried to ingest as much data as possible and produce as much data as possible. And yeah, this is just an example. If you go, for example, a data source produces, this is like a graph where each block can process only a certain number of samples. And if you, for example, produce 1,024 samples, but the next block can only ingest a certain limited number of samples, basically you have to oscillate between the blocks back and forth and check, can I produce data? Yes, no, I don't have enough data. And until the point where you have all the data ready, and then you can go to the block 3. And this context switches is a lot. And then the same thing happens also between block 2 and 3. And if you continue playing this, you get like to a latency, the minimum until the first sample gets out of 19 cycles, but for the whole processing, you can see like 2 lines in order to just illustrate the execution order, what you have. And now the thing is, if you look at this, you think like, okay, there are lots of white and blue boxes that I don't care for, that waste performance. Couldn't I do this just by reordering this way to have like a bit more smarter scheduling of the work? And here, you, for example, you have a throughput optimized where within 18 cycles, you get more data out. Or you can also select no latency is more important. You would order in this way, and then you get like a latency of 11 cycles. This problem is not new. This has been documented by Matt Ettis and also a prototype developed by Derek. And they basically created like a scheme like with floodgates that inhibited the number of samples that go into a flow graph and so on. And what we did is basically we went from this, basically the directors of each of the blocks were initially implemented inside the blocks themselves. And also in the GPU domain, for example, we're inside blocks, and we said like, okay, these blocks can't make the decisions on their own. Let's move that logic out to a central instance. We have like a scheduler that is global or per domain, and where all this logic is basically implemented there, and that allows, I know this, is in there. So with this strategy, you go from a microservice-based scheduler to a work-based scheduler where you're much more flexible and how you handle this resource constraints between latencies and throughput, and deploy also like a lot of mathematics, like in terms of graph theory. Here's some examples for the flow graphs as a challenge that are challenging for the present scheme or impossible, especially with these feedback loops. And I leave it to you like as an exercise to go through what is the best or correct, best and most efficient way how to execute these orders. Because while we implemented like 3 types of schedulers, these are just to demonstrate the API that is necessary to write your own scheduler. But there are many, many other possibilities that you could implement. And what we would like to start maybe for the next GRCon is to have like a small friendly competition to find the best default scheduler that has the best real-time throughput or latency performance for a given benchmark topology. So please have a look and maybe think about like if you would write a scheduler, what would be the best way to do so. Yeah, okay, this is just like in the end, we are supporting the Public Money, Public Code campaign. Have a look. You can also sign up individually, not just as an organization, but if you sign up individually, please convince also your boss or your organization to take part and also follow up this thing. That's very important. We want to drive further the community engagement because that's vital for this project, but we also have some improvements for the core library and user experiences that we're now ironing out to bring GNU Radio from a beta stage to a production stage. And also we have some ideas how to add a more vendor-neutral integration for GPU, FPGAs, and other TPU and other processing topologies. So the two open questions that I would like you to ponder until we maybe meet again this afternoon is, what would it take for your organization, institute, or company to publicly adopt GNU Radio 4.0? And the second question is the present license still too restrictive for GNU Radio to be used in a public organization or industry? And yeah, that concludes my talk. Thank you for your time, your patience. Sorry that I took a bit more of my time share than I supposed to. I apologize, but I guess we have like 1 or 2 questions. If not, then please come this afternoon for the general Q&A session, and we can talk in depth about each of the different aspects in detail.